In this video, we will discuss the z-test for a mean. The z-test is a statistical test for the mean of a population. It can be used either when n is greater than or equal to 30, or when the population is normally distributed and sigma is known. That's the standard deviation of the population. The formula for the z-test is z equals x bar minus mu over sigma divided by the square root of n, where x bar is the sample mean, mu is the hypothesized population mean, sigma is the population standard deviation, and n is the sample size. For the z-test, the observed value is the value of the sample mean. The expected value is the value of the population mean, assuming the null hypothesis is true. The denominator, sigma divided by the square root of n, is the standard error of the mean. Assumptions for the z-test for a mean when sigma is known. First, the sample is a random sample, and second, either n is greater than or equal to 30, or the population is normally distributed when n is less than 30. For example, a researcher believes the mean age of doctors in a large hospital system is older than the average age of doctors in the United States, which is 46. Assume the population standard deviation is 4.6 years. A random sample of $30 from the system is selected, and the mean age of the sample is 48.6. Test the claim at alpha equals 0.05. Now, to do this, we use the steps that were laid out in section 8.1. Step 1, we state the hypotheses and identify the claim. So the hypotheses are that the null hypothesis is the mean is equal to 46, and the alternative hypothesis is that the mean is greater than 46, which is the claim. So we find the critical value. Since alpha equals 0.05 and the test is right-tailed, the critical value is z equals 1.65. We just find that from our z table. I think that's table E in Appendix A. Then we compute the test value. Z is equal to x bar minus m over sigma divided by the square root of n. So that's 48.6 minus 46 over 4.2 divided by the square root of 30, which equals 3.39. And now we make the decision. Do we reject the null hypothesis, or do we not reject the null hypothesis? Since 3.34 is greater than 1.65, the decision is made to reject the null hypothesis, since that's what we're looking for here. Our claim is that the mean is greater than 46. So we're looking to see that our test value is greater than the critical value, and it is. So then we summarize the results. There is enough evidence to support the claim that the average age of doctors in the system is greater than the national average of 46. Here's another example. For a specific year, the average on the SAT math test was 515. The variable is normally distributed and the population standard deviation is 100. The superintendent wishes to see if her students scored significantly below the national average on the test. She randomly selected 36 scores as shown. At alpha equals 0.10, is there enough evidence to support the claim? Here are the scores that were selected at random. So the first thing we need to do is to state our hypotheses and our claim. The null hypothesis is that the mean is equal to 515, and the alternative hypothesis is the mean is less than 515, and that's our claim. Then, step 2, we find the critical value. Alpha is 0.10, and the test is left-tailed. So the critical value is negative 1.28. Now we need to calculate the sample mean, which is 509.028, and then calculate the z-score, which is negative 0.36 when we do all the math. Since the value negative 0.36 is greater than the critical value, negative 1.28, and falls in the non-critical region, the decision is to not reject the null hypothesis. So there is not enough evidence to support the claim that the students scored below the national average.